rules. Okay. Yeah. Hi. Never. Okay. Am I sharing? And I'm doing this. Okay. Hi. Thank you for coming back after I crushed your soul yesterday with this incompleteness stuff. I want to talk about the P versus NP problem, and I kind of do know that you probably heard about this, and but I want to tell you why we think it's a very, very important problem. And it will have to do with, efficient computation and some crypto and limitation of what we as human being can hope to know. And again, I stole most of the content from Avi Vigdersson, from Sipser, and from Scott Aronson. Those are three amazing researchers, and they also produce texts about theory of computation. So Sipser has a very nice textbook for undergrads. Scott has essays about the connection of theory of computing and physics and philosophy, and I really encourage you to read this. And Avi has a relatively new book, which is an amazing book. I cried, I laughed, and it's free and it has no proofs, only like intuitions and high level things. So it's really an amazing book. And again, I stole shamelessly from his book. So I do encourage you, it's free. You can just Google him and start reading. It's okay. Okay, so let's see what I stole from them. Okay, so we already know we're talking about computational problems, and we already know that some computational problems are just undecidable. So there is no algorithm that computes them, no Java program, and we know it's most of the space, but let's just leave them in the corner. There's nothing we can do about those. Let's talk about things that are computable, and we want to compute them efficiently. And I want to claim, we're talking about the P versus NP problem, and I want to claim that NP is kind of the set of problems that we want, and in a sense, have a chance to solve or understand. So this is one set of problems, and I want to say that P is the set of problems that we can solve or understand, that we know how to solve or understand. And the relation between them, P and NP, is kind of what is the limit of what we can know. So this is everything we maybe want to know, or we realistically can know, and this is everything that we can compute efficiently. So this talk is trying to convince you that this is the right way to view P and NP. And to view the relation between them. Okay, so let me, and another reason to care about this, about the P versus NP problem, of course, there's the limitation of human knowledge, blah, 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 but also you can get $1 million if you solve it. It's one of the 7 Clay Institute Millennium problem, along with Riemann hypothesis. So you can get $1 million. Of course, you can start ridiculous startup and make $1 million maybe more easily. But you can also solve this, and you need to kind of hurry because one of the problems is already solved. So you only have 6 to choose from, and I encourage you to choose P versus NP. But I put this slide in to just say that this, even in the global mathematical universe, this problem is a very central problem. And again, I'll try to convince you of why this is so important. Okay, so I said this like confused thing about problems we want and have a chance to solve. What kind of problems do we want and have a chance to solve? This is one of the problems that we want to solve. It's just multiplication product. So I can ask you, what is 7 times 19? And 7 times 10 is 70. 7 times 9 is one of the hardest one in the multiplicative table. But anyway, you can compute it. It's 133. And, so this is a multiplication, a product problem. I can ask you kind of the other side of this equation. What 2 primes will give you 133? And this might be harder. You need to go over all the small primes or remember the previous slide. And, it's 7 over 19. So good. Let's go for a slightly bigger example of this. what is this? So some number times some number with bigger numbers. So I don't expect anyone to do it in his head. But if I give you a piece of paper in enough time, maybe you can do it. Do you remember the algorithm we were taught in school? Every digit time every digit. This is like an n squared algorithm. Every digit times every digit. There's more efficient algorithms. You can actually do it in n log n. But you do it, and I actually ran this to see how long it takes. It takes a split second on a computer, on my computer. So, those are big numbers, but we can still multiply them pretty fast. And we know of efficient algorithms for multiplication. But now I can, again, ask the opposite question. So, I gave you the answer in the previous slide, but it turns out that it wasn't so easy to come up with the answer. Actually, the answer to this was worth $50,000. And this is the reason people factor this huge number. This huge number is called RSA 768. It has 232 decimal digits and 768 binary digits. And it's hard to factor. I think I read, okay, so this was part of the RSA factoring challenge. I think it ended by now, so you can't get money for doing this now. But I think I read that it took like 2 years for a team of mathematicians, a team of people, including mathematicians, to factor this. So it's totally non-trivial to do this. And, it was worth money. And the question is, what's so hard? Factoring, you want to factor? Here is an algorithm for factoring. Just go over, you want to factor n, go over all the numbers between 2 and maybe square root of n, right, to save a little bit, and see if I divides n. So this is an algorithm. It's very simple. The only problem is that the sun would explode, will become a white dwarf. So I Googled white dwarf. This is the picture I got, but I decided to keep it. So, if you try it for those kind of numbers, it won't end in your lifetime. So why is it that bad? It's just what we kind of do is we brute force. We go over all possible witnesses, all possible solution, all possible factors, one by one. It's an exhaustive search. It's a brute force, and it's kind of exponential in the length of n. So if I want to, the input is just this, right? Is like 768 bits. This is the input. Okay, so the input is like log n, the number of digits you need to represent n, but my algorithm takes square root of n, which is exponential in the representation. So it doesn't take 700, it doesn't scale with 700 or something, it scales with 2 to this number, which is very big. So it's just exponential in the size of my input, and a rule of thumb, exponential running time is not so good. And this is a very serious problem you should care about. And it seems that, what can you do better? Okay, there's some numbers, obviously, you can skip if you checked if it's divisible by 2. Maybe you don't need to check 4. Anyway, but how can you do much better than this? And I want to say that strange things happen. So we don't know. The short answer, we don't know. We know of something slightly better than this, but still exponential in the length of the representation. We don't know of anything much better than this. But I want to say, who knows? Problems, sometimes you can exploit the mathematical structure of the problem to come up with efficient algorithms. And I wanted to just show you this example. There's a very related, so I'm talking about factoring. I give you an integer, give me it's, let's say it's even a product of 2 large primes. I want to know the primes, the prime factors. So this is the factorization problem. You can also think about primality, which is very similar. I get a number, you just need to tell me if it's prime. Okay, so I don't need the factors, I just want to know. And I'm saying there's kind of a strange way to check primality. We actually have efficient algorithm for checking primality. Those two problems are very similar, but primality is easy, and for factoring we don't know. Here's the strange way. So I won't give you the algorithm. It's kind of it's complicated, but let me show you, kind of how it goes. This theorem is called Fermat's Little theorem. It's very useful in number theory. So it says that if you have a prime p and some integer smaller than p, then if you raise this integer to the p minus 1, you should get 1 modulo p. Okay, so this is an equation. Let's see an example. I took p to be 7 and a to be 2. So I need to raise 2 to the power of p minus 1 to the power of 6. It's 64. And modulo 7, so again, 7 times 9 is 63. Modulo 7 is 1. And it's good, right? Because 7 is prime. Yeah, please. Questions?
But this is a false theorem, right?
What is false?
Like the Fermat Little theorem. It has a little, I think there's a counterexample. Is it maybe I remember incorrectly? Like I mean, the Fermat Little theorem doesn't satisfy like all all the numbers, or like.
Google this and send me a link of what you mean. Okay.
Okay.
Okay. Let's continue and tell me if you find what you mean. Yeah. Now I understand what you mean. You mean the other direction doesn't hold. So this direction should hold. If it's prime, this should hold.
Oh, right.
Oh, yeah. You're totally right. So, okay, let me say it in okay, good. I was like, oh, math is tricky again. Okay, now I get what you're saying. The other direction. So if I want an algorithm, I need the other direction. And this doesn't hold, and that's why it's more. It's kind of harder. Yeah. Oh, this is what you meant, the GCD?
Yeah.
Yeah. The GCD. Oh, okay. But I said that A is smaller than P. Oh, this is what you meant. Okay, I see. And also the other direction. What if P is not a prime? Does the opposite hold? Okay, good. Math is stable. Got worried. Yeah, GCD is smaller than 1. You're right. Okay. But took care of this. Okay, so here's here's an example. Hopefully it works, right? And it should work because P is prime and A is smaller than P. Okay, nice. Here's another example. P is 15 apparently is not prime, though it looks prime. But 2 to the 4th, so I need to take 2 to the power of P minus 1 to the power of 14. It's this number apparently, and I took it mod 7, it's 4, and it's not a 1. And now I have kind of a proof that 15 cannot be a prime. Okay, because if it was a prime, I needed to get a 1. So I kind of get a proof that this is not a prime number. But I didn't get the factors or anything. I didn't factor this number, but I know for sure that it's not prime. Something going on in the chat. Yeah, so this is Lucas. Okay, I'll read the check later. There is the opposite direction also roughly works. Okay. Let's concentrate on this. Okay. So what I got, what I want to say is, this is kind of a proof, a certificate that 15 is not a prime number because, Fermat Little theorem is not working. So I can produce proofs that something is not a prime without giving you the factors, which is, for me, it's kind of surprising. And I need to know something about the mathematical structure of numbers. And you can convert these ideas to polynomial time algorithms. It's actually not so easy, and it requires lots of other ideas. And we only know of a polynomial time algorithm. I think this was done 20 years ago, 2002, something like this. So we're very kind of recently, we found how to convert those kinds of argument into polynomial time algorithm. Before this, we had probabilistic polynomial time algorithms, but even those are requiring more tools. But anyway, you can see that I can sometimes certify this. I can understand something about the mathematical nature of the problem and not just, go over all certificates. Okay, so this is what I wanted to say about primality and factoring. I want to show you the algorithm, How do I make this toolbar go up? Put it somewhere else. This toolbar is in the middle of everything. Okay. Okay, so, maybe it's not so easy to factor, but why would someone pay you a lot of money for factoring? So the company that was paying this, that was creating this challenge, is the RSA company, and their product is an encryption scheme that you can break if you can factor numbers, if you can factor integers, and they kind of want to know what's up there. And RSA is currently the leading encryption system. If you go online and you go shopping online, the thing that protects your credit card is RSA, most likely. And if you can break factoring, if you can factor numbers, then you break it. So every time you shop online, you kind of, you trust that you cannot factor numbers efficiently. And many other cryptographic constructions are based on this factoring assumption. Let me show you one of them. So I think Yael talked about this. I don't think she showed RSA, but maybe Diffie-Hellman. She showed related encryption stuff. So I don't want to do encryption. Let me just give you a very quick example of how you can use factoring or hard problems to get a crypto primitive. So this is the easiest example I could come up with. This is an example of how you get secure password system, assuming that it's hard to factor numbers, but easy to multiply them. So, relating to Yael, we believe that multiplication is a one-way function. Okay, it's easy to compute and hard to invert, or at least many people believe that. So here is secure password system. Suppose there is a server and you're a user and you want to create a login password so you can log into the server. And the question is, what's going to happen to this password, right? I have a password. I come up with, I rule. I send it to the server. Where is it stored, my password? So it can be stored on some file somewhere, right? But then if someone breaks into the computer, he knows all the passwords, right? So it's kind of a bad idea to just store the password. But what you can do is just not store the password, store a byproduct of the password. So here is how you can do this. Let's assume that the user select as a password 2 large primes. I mean, it can be a string, but we'll convert it to 2 large primes. The server will only store the product of those two. Okay, so it will store P1 times P2, and will never store the original password. Will not store the 2 large prime, just their product. And then to log in, the user will send the password, which is P1 and P2, and the server will compute P1 times P2 and compare to what he has stored. And now the server, it doesn't have to be a secret. P1 times P2, the server can just publish, right? It can be out there. But what is actually protecting the password is the fact that you can't factor. So if you're a good guy, like the server is a good guy, only needs to do the multiplication, which is computationally easy. But if someone wants to steal your password and pass as you and log in as you, it needs to, factor this large number, which is, hopefully hard. I don't know if hopefully, let's talk about it later. So this is how and you can do it with other, one-way functions, of course, but factoring is like a very useful building block. Okay. And let me show you other problems we care about. I'll show you a bunch of problems, and we'll talk about whether they're hard or easy. Here's another problem from a different, from different field in mathematics. This is about graphs. Before we saw something about numbers and primes. So this is about graphs. Give you 2 problems. I think you probably have seen them. It's about finding passes or telling whether the pass exists or not. What is an Euler path is a path in the graph that uses each edge exactly once. And a Hamiltonian path is a path in the graph that uses each vertex exactly once. Okay, so they're very similar, but in one of them, you need to go over all the edges exactly one, and the other on the vertices. Again, I don't know what to do with this toolbar. Okay, so let me show you a Hamiltonian path here. Okay, I think I visited all the vertices. And here's an Euler press. It's slightly harder, but I did find it. It goes like this. You can see the pink and like this. Okay. Okay, nice. So this seems more complicated, but still, I can ask, do I need to brute force? Do I need to go over all passes? There are exponentially many passes, like this can be first and this second, so on. Exponentially many, right? I need to take all orders of the vertices, maybe. Maybe I need to go over n factorial things. This is too much, but do I have to? For Euler press, it turns out that you don't need to. There's a very cute characterization. Apparently, there is an Euler path if there exists an Euler path exists if and only if all vertices or all but exactly two vertices have even degrees. Okay, so in our example, and you can turn it into a polynomial time algorithm. Okay, so just checking that this condition holds is, well, depend on the representation of the graph, maybe n squared if you have adjacency matrix. You just need to know the degrees. So in our case, this is degree 3 and 3, so those are odd, and this is 4, 4, and 2, so those are even. So exactly 2 with even degrees, and we did find an Euler path. What about the very related problem of Hamiltonian paths? We don't know. So you may recognize this as an NP-complete problem. I'll talk about those. But you see, those are very similar problems, but we found a trick for Euler paths, something about the math, something about graphs that guarantee the existence. And we didn't have to go over everything. So good for us. And we don't know of such a trick for Hamiltonian paths. And we can kind of roughly define the class P now as the class of problems of, it's actually a decision problem. I'll talk about it later. It's a set of problems or class of problems that have polynomial time algorithms. And we are, as complexity theorists, we think of polynomial time as efficient. So every time I say efficient, I mean, or easy, I will mean polynomial time. And every time I say hard, I mean non-polynomial time. And there's definitely some criticism of this decision to think of P as efficient. So is n to the 1,000 really efficient? To n to the 1 million, is it really efficient? Is it more efficient practically than 2 to the something very small? So this is I think this criticism is is very real, and it makes sense. I want to say a few things about this. The first one is we don't see so many n to the 1,000 algorithms. So yeah, you can craft something that will be n to the 1,000, but the problems we deal with are usually smaller problems we care about are typically smaller polynomials, and there is this phenomena that once we found a polynomial time algorithm, we can typically reduce it down to a really reasonable polynomial. So this is, for example, what happened with factoring. It used to be with primality testing. The first paper had a high degree polynomial, and now it's much more manageable. So we're kind of good. Once you have polynomial time algorithms, we're kind of good manipulating them. This is one reason we care. We like P. Another reason is you can compose, if you have two subroutines that work in polynomial time and you compose them, it's still in polynomial time. So we have this closure property that we like. And if we say efficient is n or n squared, once you compose it, you get something of higher degree, and it's very hard to work with. So it's something we can work with, is another reason we like this definition. And the other, maybe another reason we like this definition that turned out to be false, but originally, I told you last time about the Church-Turing thesis that says that everything you can compute on a physical machine, you can compute with Java or you can compute with Turing machine. And we believe the Church-Turing thesis. Unfortunately, so there was a version of the Church-Turing thesis that talked about P. It says that everything you can compute in polynomial time over a physical machine can be computed in polynomial time by Java or by Turing machines. So if you can do something in polynomial time, you will be able to do it with your restricted Java or your restricted Turing machines. And unfortunately, we now conjecture that this is false. So we can, we can't falsify it yet, but we now believe this extended conjecture is false. And this is due to quantum computers. We know that quantum computers can factor integers in polynomial time. This is called the Shor's algorithm. However, we believe that you cannot do it with a classical computer. So again, when we say we believe, it's not a consensus, I guess, in the community. Some people believe that you can factor. However, I think the majority of us believe you cannot factor in polynomial time. So it's very likely that the extended Turing thesis is wrong, but this was part of the original reason why we liked P so much. We thought it was stable. And it is stable to some extent. It doesn't, if you do Java versus Turing machines, one is random access, the other one is not random access, okay, but it will still be, if this is polynomial, this is polynomial. So for many models, we did see this phenomena that, you may blow up your algorithm by a polynomial factor, but not more than this. With quantum computer, this might be changing, but still there's some stability to the class P, and our kind of approach is let's kind of understand the order of magnitude, and then we take care, if it's in P, let's take care of this. But still, first try to understand if it's even in P. Okay, so this is P versus NP, and many interesting problems are in P. I'm sure you saw this, like matching, and I gave you some example, primality. And some of them require clever insights, like primality testing and Euler. You need to know something about the mathematical nature of the object you work with to say that something is in P. And you can ask whether all interesting problems are in P. Okay, so there's some stuff that are undecidable. Some stuff are crazy, obviously, but is everything reasonable in P? And again, I need to tell you what's reasonable. So let me give you some more example of what I find reasonable and I want to solve. And those are search problem. You're looking for something. So here is one search problem. So we've seen some of those things, right? Factorization, Euler path, all of those are, you're looking for something. Here are more of those. You want to do pattern matching. I give you a subsequence, and you want to find it in a larger sequence. Maybe this has to do with DNA or something. You want to prove theorem. I ask you to find a 200-page proof of the Riemann hypothesis, but I can actually turn this into formal language. I can say, this is the set of all problems, of all sentences in piano arithmetic for which there exists a proof in piano arithmetic of length, this and that. So I can actually convert this into a formal language. But definitely, if you know something, given what I told you about last time about axiomatic systems, you can just say this is a sentence or this is a theorem. I want a proof of this length in this axiomatic system. So theorem proving, right, is something that we care about, and we're looking for a proof. Here's something else we care about: linear programming. So you get a bunch of linear inequalities. They kind of give you a high-dimensional convex body, and you want to know if there is an integer point whose all coordinates are integers inside this body. Maybe you want to solve Sudoku, right? Every column, every row, and every column need to have all the numbers between 1 and 10, and you can generalize, right? You can do Sudoku with the n rows and columns. This is a different problem called a knot. I give you a knot. This is actually a really cool field in mathematics, knot theory. I give you a presentation of a knot. I don't know this. And you need to untie it. It's not really tied, right? And you need to kind of stretch it so it will untie. So I was trying to give you crazy stuff from different branches of mathematics. Okay, computer science, optimization, whatever. Those are things we care about in mathematics. Yeah, please.
Is pattern matching not known to be in P?
Oh no, it's definitely in P. I'm saying I care about this. Yeah.
Okay,
Like,
okay.
okay.
Oh,
I'm not saying those are hard. Some of them are hard. So linear
mhm.
programming is hard. Sudoku will be hard. Proving theorem is hard. Unknown, we don't know. Uh, very few we don't know. Pattern matching definitely easy, right? Just go n squared. I mean, yeah,
Yeah.
it's easy. So some things I talked about are easy. This is what I'm trying to say. Some are easy, some are hard. Looks kind of random, which are easy, which are hard. I think is something going on here. Yeah. So what's common to all those problems? Oh, I gave you the answer. Okay. Uh, as you hinted, they don't necessarily have the same running time. So pattern matching is polynomial, is like n squared. I don't know. How do you prove theorems? Who knows? How do you do linear programming? Probably hard. Maybe it's 2 to the n. Maybe so it's not the same computation. It doesn't require the same computational power, maybe. But what I want to say that those things have in common is that solutions are easy to check. So once I tell you the sequence starts from here, you check it. Once I tell you, oh, here's a proof for Riemann hypothesis, or this is the theorem you gave me, here is my formal proof, and you go, well, this is really an axiom. This is really, if you take the second and the third sentences, it gives you the fourth, and so on. So you can think of a computer program that checks, and this should be polynomial time. Again, once I give you an integral point and I give you the assignment, then you just check that it satisfies all equations. And Sudoku you can check, maybe linear in the size of this table. And if I tell you how to unknot and knot, hopefully there's a formal language to reason about this too, but you can check it. And so you can check the solutions. So for some of them, it's also easy to solve, like pattern matching. I can do it in polynomial time myself. I don't need you, but I can check. But some things might be hard to know, to come up with a solution, like to prove theorems or to solve a linear program. Uh, hmm, okay, I see. I call it linear programming. It should be integer programming. Sorry. Oh, this says it. Okay. A linear programming is actually not hard, but this should be integer programming. To find an integer point is hard. Is NP complete? Anyway, once I give you the solution, oh, I see. This is integer and this is linear. Okay, so I need to choose one. Anyway, once I give you the solution to those things, you can verify efficiently. It may be hard for you to solve, may or may not be hard for you to solve yourself, but will be easy for you to verify. And this is, I'm claiming, really captured the notion of, this is the heart of NP. NP is a set of problems for which there is a polynomial time algorithm for checking a given solution. If someone, a Martian, solved it for you, you can check. Okay, if your friend prove a theorem, you can check his work. And it's easier, it might be or may not be easier than proving it yourself. And I'm kind of confusing a little, I'm confusing a bit the terminology. NP is a set of, formally it's a set of decision problem, not of search problem. So, factoring, as I stated, is not NP. If you want to convert it to NP, you need to say whether this number has a prime factor larger than K. Okay, so typically you can convert search to decision, not always. So let's stick with but for this talk, it doesn't really matter. Okay, so formally it needs to be it's a set of decision problems. And I want to say those decision problems, as I already said, they have the flavor of finding a needle in a haystack, or like it seems that maybe you will need a brute force, go over everything. So this is the picture we usually put in those talks, right? There's a needle somewhere, go find it. There's a Hamiltonian Path. One of the passes in Hamiltonian, which one, what? But if someone points you to the point, right, it shows it's here, you say, oh, this is a needle. Oh, yeah, this is an Hamiltonian Path. True. This is a solution to the Sudoku puzzle. So those are the kind of problems that NP really captures. So this is the famous P versus NP. Again, P is a set of problems, decision problems for which solution can be found efficiently. There's polynomial time algorithm. We can find it. NP is when the solution can be checked efficiently, not necessarily found. Okay, and P versus NP is about, whether finding is actually harder than checking, which is kind of, naturally you believe this, I think, if you have any experience in life. Finding a proof should be harder than verifying a proof. Okay, depends. If it's your students, maybe, okay. But morally. So this is what P versus NP is saying. P not equal to NP will say that finding is like strictly harder than checking a solution. Okay, and again, I want to go back to this diagram. I didn't put, I didn't have the slide again, but this diagram that, or the first slide I had, where I said NP is what you want and P is what you can solve, and whether those two things are the same. So why are we so obsessed about this NP thing, this NP class? Why is it so important to us? Sure, it's things you can check, but that is so important to check. I want to say that this is like a universal phenomena. P versus NP is central not only to computer science, but to math, to other sciences, to technology in general. And I said that kind of what people do have, the problem people are interested in have NP flavor. So here are some examples, abstract examples. So as mathematicians, what are we doing? We talked about this. Someone gives you a statement, you're trying to find a proof. This is your job, find a proof. Maybe also come up with a statement, but let's forget about this. What our scientists do, like in a very abstract level? Maybe they collect some data about a phenomena and they want to find a theory that explains it. Okay. What are engineers doing? Maybe they have a bunch of constraints, budget, size, weight, whatever. And they need to find a good design of a bridge, of a cell phone, of something. But what is kind of happening is that in those kind of challenges that humanity faces, checking should be easy. So if I give you a good proof, you should be able to verify it. If I give you a good theory, you should be able to say, oh, that looks like a good theory. If I give you a good design of a bridge, you should say, yeah, this bridge has a good design. Hopefully you can do this, not always. But if you can, then, what's the point? What's the point of looking for this object if even when you find it, you don't know? If it slaps you in the face, you don't know it's a good object, right? So why are you looking for this? What are you expecting to gain? So this is why I'm saying that NP is what you hope to do, is like something more universal than just computer science. This is what humanity is trying to do. It's trying to find something. And typically those are things that when you see them, you say, oh, this is a good thing. You can at least tell it's good. It's not always the case, but I want to believe that most of the time this is the case. So this is but you can see that if P is equal to NP, we have fast automatic finders. We can find stuff automatically. And unfortunately, it will also mean that mathematicians are out of a job because you can just find proofs. And this is, finding them is as easy as verifying. So you don't really need mathematicians. Okay, so again, this is some piece of philosophy about like, why are we obsessed with NP? Why is it really, a global thing? This is capturing what humanity, many things that humanity is trying to accomplish is kind of captured by the NP complexity class. Okay, and let me talk a little bit about universality and NP completeness. So we've seen problems. I told you a bunch of problems. Some we knew are in P, are easy, but what about the other ones? Like, okay, so we said Euler Path, I give you an algorithm, pattern matching gave you an algorithm. Okay, what about the rest? Sudoku, Theorem Proving, a bunch of other things. Are they easy or hard? So again, as I told you, how did we do the polynomial time algorithms? Sometimes we really had to know something about graphs, about numbers, and then, from the mathematical structure, we can deduce an algorithm. And this was not easy. So maybe we need to tackle those things one by one, understand the structure and try to come up with a different algorithm for each of them. Again, when I say hard, I mean non-polynomial time. Easy will be polynomial time. I want to say that maybe we don't have to. It turns out that those problems are intimately related. There's a very strong connections between them in the following sense. If Sudoku is easy, if you find a polynomial time algorithm for Sudoku, then you have a polynomial time algorithm for theory proving, for Hamiltonian path, for factoring, which is if you haven't seen this before, this is striking. This is just because Sudoku is NP complete. I won't show you a proof of this. Hopefully, they teach you this in your school. But and it's those are really beautiful proof. Even the idea that if you solve something, everything else is being solved. It's very beautiful. This is a Cook-Levin theorem. But Sudoku is what we call NP complete, and the meaning is that if you can solve Sudoku, you can solve any NP problem, and those are all NP problems. So if you solve Sudoku, you solved all of them. Again, I think this is striking because Sudoku is nothing like theorem proving. It's nothing like Hamiltonian Path. It's nothing like factoring. It's not from the same field. This is why I try to give like random problems. They're not connected, right? Or are they? And but it turns out that they are in a computational sense. And the way to reason about those things is through the idea of reduction. So it turns out that you can take a theorem you want to prove and transform it into a Sudoku puzzle. And once you solve the Sudoku puzzle, you have a solution for your theorem. You have a proof for your theorem. So you can go from theorem to Sudoku and from solution for Sudoku to proofs. And this is true for everything I listed in there, everything in NP. You can convert Hamiltonian path to puzzles. You can factoring problem. You can convert to Sudoku and so on. So this is, again, I think it's striking. Very different problems, and somehow their solution may be related. Okay, so we know that P is equal to NP if and only if Sudoku has an efficient algorithm. It all boils down to this. This bridge finding is about Sudoku now. And this also means that maybe we don't need, if Sudoku is easy, if there's an efficient algorithm for Sudoku, then we don't need clever insights to do the rest of them. It will all fall into place. We won't need any clever things to say, right? We only need to solve Sudoku. Of course, we don't believe that there's an efficient algorithm for Sudoku. And the next thing I want to say is that, you may think, again, you may have seen that, and or if you haven't seen that, you can ask yourself, like, what's so special about Sudoku? It's just a random thing, right? And it turns out that there are many, it's not a unique phenomena, the Sudoku thing. There are thousands of NP complete problems that we know about from very different fields. I'll show you some from biology, from physics. You can Google and, NP completeness and, physics, and you find, or chemistry. Each of them, you'll find many problems. So there are many such problems. If you solve one of them, if you give an algorithm to one of them, you have solved them all. And those are even less related than this, right? They come from different areas. So this kind of leads me to the next discussion. So again, I don't want to do proof so much because I think reduction you have seen or you will see in your school. It's a technical thing that is, again, sometimes very beautiful and insightful. But I want to kind of talk more high level now because I think the technical issues are being taught. And the reason you find it anywhere is because computation is universal. So far, when I say computation, I meant a Java program, a Turing machine, something that manipulates bits maybe, but it's actually, computation is done everywhere. It's a universal global thing. What is a computation? Let's say it's every process, which is a sequence of simple local steps. Okay, so it manipulates small objects or pieces into something bigger. This is not well defined, but you can think of many examples. Bits in computer is one thing we've been talking about, right? Java programs, but also atoms in matter, cells in tissue, neurons in your brain, individual in population, in social media, and so on. You can think of many natural things, many things that you care about as small pieces, small object or entities that are computing something. And so therefore, it's kind of not surprising that we see NP problems everywhere. So here are some lists in biology. or NP-complete problems even everywhere. In biology, for example, protein folding is an NP-complete problem. So protein is like a sequence of amino acids, and some bonds are more rigid than others, and this kind of tells you how this can fold. And you want to fold it into a 3D you want to fold it into the 3D structure. And apparently, I mean, many variants of this problem are NP complete. In physics, you can think about the surface area of a foam. I'll talk about this in a minute. In economics, you can think about the market equilibrium and things like this. And those will be NP complete problems that we think of as hard problems. There are many more. But when you see this, it's kind of disturbing because it seems that nature is solving those problems. So can it solve this? Can it solve NP-complete problems? So some people believe this. You can find reasonable papers claiming that they solve P versus NP using some natural phenomena, but we don't believe this. Well, let me show you one concrete thing that someone tried. So here's an NP-complete problem. Okay, it's called it's called Steiner problem. In this problem, you get a bunch of vertices or bunch of points in the plane, and you want to connect them by segments such that the total length of the segment is minimal, whatever. Okay, so this is an example, and I can connect them. I don't have to have a point up here. I can just connect them like this. And this, this has to do with surface area of foam. You want to minimize surface area, and also, maybe those are stations, and you want a train track to build train tracks that will connect them. It comes up in practice. And I told you this thing is called a Steiner tree. And this thing is called Scott Aronson. Again, he's a leading researcher at UT Austin doing theoretical computer science. His field is quantum computation. But at this particular picture, he's trying to solve this NP. So a Steiner tree, by the way, is an NP-complete problem. And Scott is trying to solve it with soap bubbles. So there's a kind of a piece of folklore that I kind of believed that soap bubbles can solve Steiner trees. So the way you do it is you take two glass plates with pegs between them, and you dip it in soap water, and you take it out, and then the bubbles will form to give you a Steiner tree. They're trying to kind of minimize the surface area. So they'll give you a Steiner tree. So this is Scott. I guess he's in class. You can see in the background that he was trying to do this Steiner tree. And he dipped it, And Scott's conclusion, you can read about this in his essay papers. His conclusion is that it does work when you have few pegs, maybe 3 or 4, it does typically work. When you have more pegs and it's unclear, sometimes it will give you something correct. Sometimes it will not give you any Steiner tree. Sometimes, so you can't really, it doesn't really solve it, which is too bad because we were hoping that soap bubbles can do Steiner trees, and then since it's NP complete, they can prove theorems and they can do everything. But according to Scott, I haven't tried it myself, but Scott is saying it doesn't really work, which is okay, maybe not a surprise. But also he has a caveat. He's saying he didn't try all brands of soap, so maybe there's still hope. But anyway, and you can see other natural phenomena happening that seem to solve NP hard problem, like proteins are being folded in a good way, I guess. Water is finding like the steepest way to go, things like that. But what can explain this thing that natural things seem to solve very hard problem? So it can't be that P is equal to NP and they found a polynomial time. I mean, we don't expect them to run exponential time algorithm that fast. So it might be that P is equal to P and they found this, and they found a solution, and we just need to see what they're doing. Although we kind of don't believe that. We believe that sometimes it's just our model is wrong. This is not really the problem they solve, or sometimes they solve it for special cases. So protein folding for animals that actually exist cannot be that crazy. There's no local maxima or minima. So it seems maybe they're solving like a very special instances that are easier to solve. Maybe they only approximate the solution. So we mostly do not believe that nature can solve p versus can give polynomial time algorithms and is actually solving those problems. It's something about the modeling, about what they're not actually doing what we conjecture them sometimes to be doing. Okay, so this is about nature. I'll talk about nature again in a few minutes, but I wanted to, if we have time, I want to talk about something, a different angle. So I'll go back to nature, but I wanted to talk about, to go back to this P versus NP problem and this hardness thing. So we don't believe nature is solving this. We believe those problems are really, really hard. And there's no polynomial time. I believe P is different than NP. And this is too bad. And we need to cope with this. I mean, sometimes it's things we really need to solve, and we come up with ways. Maybe we approximate, or maybe we find an algorithm that works in special cases, and so on and so forth. But I want to say that hardness is not really bad. Intractability is I call it is a frenemy, is a friend and an enemy. So obviously an enemy because you solve it and you want to solve it and you can't, and it takes a lot of risk. So SAT solver is something you want and is very hard to get. So obviously it's bad, obviously it's an enemy, but I want to say it's sometimes a friend. And you kind of seen this with the L. So the first the most obvious reason it's a friend is because it allows you to do crypto. Harness assumptions, one-way function. The assumption that a one-way function exists is formally stricter than P versus NP. So you at least need that P is different than NP for one-way function, and one-way function is kind of underlying. It at least what you need for most of cryptography. And I kind of gave you an example with this password thing that you can use. You can really use hardness as your friend. Good guys will do something that is computationally easy. Bad guys will do something that is computationally hard. This is replacing secrets in primitive or in pre-modern cryptography. So it really allows you to do crypto, which we like. And if you can do, if factoring is hard, you can do all of those things and many more things. And I think Yael talked about some of them. And definitely crypto is the big plus of harness. Let me talk about a different plus of harness. So, okay, cryptography will be one good thing we get from the fact that P is probably from the conjecture P is different than NP and that one-way function exists, all those hardness assumptions. Another example of why hardness, intractability is a friend and not only an enemy is the concept of derandomization. And this again has to do with things that Yael talked about. I'll talk about them from a slightly different angle. So she talked about the cryptographic angle. I'll talk about the kind of more complexity angle. The idea of derandomization, I have a slide about this, but it's basically you take a randomized algorithm and you want to convert it to a deterministic algorithm. Can you always do this? This is a question of derandomization. And we'll see how intractability plays a role in derandomization. But before I tell you about like the theorems there, I wanna go back to this idea of randomness again. So randomness has philosophical aspects. What is really random? Does randomness exist? And so on and so forth. I don't want to get into this. I want to talk about, is randomness helpful to us? And we've seen yesterday, I gave you one definition of randomness, okay? Kolmogorov complexity, I gave you, what is the Kolmogorov complexity of a number or a string? And, we had a definition, minimum Java program, and so on. And note that this measure is objective. It doesn't matter who measures this. It's like a function, k of x is, we define what it is, and it's an objective measure. And there are other measures, and most of them are kind of objective, just a number that is associated with our string or so on. But I want to claim now that randomness is not necessarily objective. So we'll play a fun game. So here's okay. I wanted to do this with a coin and everything, but I don't think I have to take off my background. Anyway, let's mentally play this game. This is me. I'll toss a coin. This is you. I know it's like this starts at like 8 a.m. in some places, so you're maybe tired. But the game is I toss the coin, and you need to guess what is the probability that it will fall head. Or okay, oh, you need to guess. If it's head or tail, I ask you what is the probability of head. You know, are likely to tell me that it's 1/2. This is unbiased coins and everything is valid. It should be 1/2, right? Now I tell you, okay, so you know what? You can use your computer before you answer. Yeah, use your computer, your laptop. You're like, okay, it's still 1/2. What do you mean? I say, okay, now you know what? I give you a bunch of cameras, maybe a supercomputer. I'll give you, maybe you know all the physics in the world and everything, all the laws. Now you tell me. And you can take pictures and the temperature and the humidity and the wind and everything. And now you need to tell me head or tail. And you take pictures. Maybe now you can tell. Maybe you do the calculations with all the variables and and maybe you can tell me exactly. You can predict if it's head or tail. So what did I give you? I gave you computational power. I gave you knowledge. So what I want to say is randomness in this example is not objective. Randomness is in the eye of the beholder. It depends who you are and what is your, actually not in the eye, in the computational power of the beholder. If you don't have any resources, sure, this phenomena looks random to you. Yeah, it's a random, it's a random coin, right? But if you know everything and you're very equipped, you have computational power, maybe this is an easy problem now. Maybe you can tell that this bit is, you can say, oh, this coin toss is not really random. I know the answer. So again, this is a kind of a philosophical idea that we're going to use in the next slide. And kind of the take-home message is randomness can be subjective. It depends. Random to who? To someone who knows a lot or to someone who doesn't know anything? And the answer may change accordingly. Okay, so again, this is piece of philosophy, but we can actually use this to de-randomize computation. And this is the paradigm of hardness versus randomness. So here is a question. Can randomness speed up computation? So, so far I talked about the class P. Oh, let me do this. I can define this class called BPP. Those are set of decision problems with polynomial time algorithms. When I allow the algorithms to toss random coins, they can toss coins, they can use random bits, and they only need to be correct with high probability. So maybe with small probability, they can have some, probability 1%, they'll make an error. Okay, and you can toss coins, and if the coins are, I don't know, all tails, maybe it's bad for them. Maybe they make a mistake, but 99% they'll be correct. This is the class BPP. It's kind of the analog of P when you can toss coins, and we believe we have coins. You can toss them. Why not? And the question is this making things much easier for us? Maybe there are hard problems that are now easy. And in fact, there are some BPP problems that we don't know P algorithms for. So sometimes we know randomized algorithms, and we can't find a polynomial time algorithm. So this was the case for primality checking, testing. We knew of a randomized algorithm, and it took us a lot of time to find a polynomial time algorithm, but we did eventually. But there are still problems for which we only know BPP algorithms and not P. So again, I listed some. Volume estimation is, let's assume you have a convex body, some polytope in high dimension. And let's even assume that it's, kind of bounded by the unit cube. So it's a top in high dimension. I want to know the volume of this thing. So you may think it has to do with geometry, and sure, you need to know some geometry to do this. But if I give you random coins, there's an actually very easy algorithm. If you want to estimate the volume. you just choose random points in this unit cube. Sorry, I probably had to put a picture. I was too lazy. But you just choose random points and you use your randomness as random points in this cube, and you see how many of them lie in the body. So it's easy to know, to tell if a point is in the body. You get the body as a set of linear inequalities. So anyway, you just subsample. It's just sometimes we call it a dart algorithm. You throw darts at this and you see how many land in the body. And the fraction that land in the body is your approximation. It's very easy. I don't need to know anything. It just, darts, and I approximated this. If I have randomness, I can generate primes. Let's say I tell you I need a prime number with n binary digits, or let's say between n and 2n binary digits. Find such a prime. Maybe you need to know how primes are distributed. We don't know those things, right? But if you have randomness, you just randomly select a bunch of numbers, and you know by the prime number theorem that if you select a few of them, one of them is likely to be a prime, and you can test if it's prime. So just randomly generate them, and I'll find a solution. Solutions are not rare. I'll find them. But if I need to go one by one, maybe I need to go for a very long time. I don't know how they're distributed. So to get a polynomial time algorithm, maybe I really need to know something about primes. To get a BPP algorithm, a probabilistic algorithm, I need to know much less. I listed another problem. There are more of them. This PAT is polynomial identity testing. I give you two polynomials written succinctly, like maybe x plus y times z plus y times. Okay, they're not explicitly given. So two of those, and I ask you if they represent the same polynomial. So this is kind of hard to reason about. Maybe you need to expand them, and the expansion is very long. But if you have randomness, you can just evaluate them on a few points, and we know that if they're the same polynomial, we'll always get the same number. But if there are different polynomials where we should not, they shouldn't. Most of the evaluation should be different. So this is this is called Schwarz-Zippel. Anyway, you just need to sample a few points, check if they're equal on a few points. This is very easy, evaluate on a few points. So what I'm trying to say is that, yeah, those are problems we care about. Again, different parts of mathematics and derandomization. So randomized algorithms, like, just sample a few, just, try a few assignments, sure. But derandomization seemed to really require deep mathematical insights again. So you may conjecture, after you see this, you may conjecture that P and that BPP is different than P. How do you do this? You need to go again one by one and reason about primes and reason about geometry and reason about polynomials. And what I want to say is you probably don't. And again, this is, if you haven't seen this, this is absolutely striking. And this is tying hardness with randomness. So here's a theorem. We actually proved this. There's only small cheating in the assumption here. I wrote it here. But if you don't know what it means, circuits, and forget about this. The theorem says that if there are hard problems, it's roughly P not equal to NP. Something slightly stronger than this. So if there are hard problems, then randomness is not going to help you. Oh, okay. So this is called the hardness versus randomness paradigms. The existence of hard problems of a specific kind, doesn't have to be SAT, it can be any other problem with an algorithm in E. Anyway, if there are a hard problem, then randomness is not going to help you. At least not going to give you something more than a polynomial speed up. So why? What's the connection between hardness and randomness? And it's kind of very hard to give up on both, because it seems that we really believe that some things are hard. We tried and we can't get them, even empirically. And it does seem that some things, that randomness does help us for some computation. Sorry, yeah, please. Questions?
Yeah, but I think can we build, I think we can build a pseudorandom generator based on hard functions, right?
Yeah, okay, so I want to, yeah. So yeah, let me connect to what Yael was saying. I think you've seen something like this with Yael. there's a slight difference between pseudorandom generators for complexity and for um, and for crypto. But I'm not trying to get into this. This is exactly true. This is exactly, so we all kind of yeah, she stole my thunder. I should be first. Okay. But it's the same kind of phenomena she was talking about. I just want to make it explicit and stress. It's exactly what you were saying. You have one-way function. You can build a pseudo-random generator. I'll say it next. For us, the assumptions are going to be different, and the pseudo-random generator is slightly different. I wanted to say that this is another application of pseudo-random generator. She was talking about pseudo-random generator to do crypto with. I want to say that pseudo-random generators can de-randomize this class BPP. So exactly, very, very good point. I should have said this. So yeah, maybe you're not surprised because again, Yael stole my thunder. But think about when Yael says like it's the connection is striking that there's that randomness. It's a different resource, right? There are many resources, and actually, complexity theory is the study of what you can do with limited resources. And I mainly talked about time, but you can talk about space, you can talk about randomness and information and query and communication and other things. But, P is about, it's a different resource. It's about having someone prove something to you. And BPP is about tossing coins. And it seems unrelated. Why would hardness gives you randomness? And okay, so this is and again, what's weird is you kind of see reductions in your life, but typically they say if one algorithm exists, another algorithm exists, right? This is saying if something does not exist, right? There's no efficient algorithm for Hamiltonian paths or for SAT. Or if there's no algorithm for something, P is different than NP. So there's some problems we cannot do in P. If something does not, some algorithm does not exist, then another algorithm does exist. Then you can, you have an algorithm for generating primes, polynomial time algorithm for generating primes. If something does not exist, something else does exist. It's a very weird thing. And again, this was the state of affair for Yale too. Okay. Yeah, please.
Excuse me, why do we have to exclude circuits of size 2 to the power of order n? Because if I remember correctly, circuits were not universal. Why do we even have to worry about them? We,
Yeah, I
um,
don't want to get into this. This is there's a technical issue with the construction. Again, it depends on the type of pseudo-random generator you're trying to get. So for complexity, we typically have this assumption about circuits. I need the non-uniformity.
mhm.
Let
So
me
it's
not
not,
get into this. Okay, I can do it offline.
yeah, okay, thank you.
Okay, but again, I want to think about yeah. So you obviously know more. So specifically, you know what are circuits. But I want to go to the high level. That's harness. If there's something hard, then there's something else that is easy. And it's like you kind of need to choose if you like your mom or dad more. I don't want to say my answer because this is recorded. But we're choosing hardness over randomness. We choose to believe that there are hard problems, P different than NP. I don't know about this specific assumption, but if you're worried, you can relax this assumption a little bit and get slightly worse generators. So we can negotiate about this assumption. But we do believe that there's something that is hard, that P is different than NP, and then we have to sacrifice something, and we believe that P is equal to PPP. So we believe that there is all of those things can be solved in polynomial time. We have no idea how. There's some reasons we've been combating with both hardness and randomness for a long time, and we're more successful in derandomization. Many problems for which we didn't know, we knew a BPP algorithm, we now know a P algorithm. We have less success with P versus NP, and we feel it's kind of a deeper thing. So, we choose to believe that hardness exists and that randomness is in this specific way not going to help you. We do know that in other models it's essential. Like in crypto, you have to have randomness. Like in I don't know, communication complexity. In other fields, we do know, for other resources, we know that randomness is making a difference. For computation, we believe that it doesn't give you more than polynomial speed up. And again, this is the kind of, so the idea of how to do this is pseudo-randomness. And Yael talked about this. Let me do the slide kind of quickly. It's related, but not exactly the same. So I want to say that hardness, if you have a hard problem, this should imply general derandomization. So here's an example. If you have a probabilistic algorithm A that runs in time n squared, I should be able to give you a deterministic algorithm with maybe slightly worse running time, but still polynomial. How can I hope to do this? I need to assume that I have a hard function. This is where the P versus NP comes into play. It will give me some hard function, and I will massage it into a function that can be computed in time n to the 10, but cannot be guessed. The answer, I can't guess the answer with good probability in time n squared. So how to take this into this, or the assumption I had before into this, you do something. But this is you come up with, you have this function f that can be computed in high polynomial time, but not in low polynomial time. And then what my new algorithm, the deterministic algorithm, is going to do is it's going to produce bits or things that look like f of x, right? It will evaluate f on different x's, and we'll feed those things to A, and we'll tell you know what, those are random bits. They're not really random. He produced them, right? But they will look random to A. And then A will operate correctly. So it will kind of will come up with pseudo-random bits, and then we'll feed them to A, and A cannot tell pseudo-random bits from random bits, and will operate correctly. And then I'll de-randomize A. And again, the idea is that f of x looks random to A, even if it knows x, right? The same as in Yael's talk. Because I don't have, A doesn't have the computational power to compute f of x or to guess f of x. They're not random to A prime. He produced them. They're not actually random to this A prime guy, right? So this is what I wanted to demonstrate, that randomness is in the computational power of the beholder. It does look random to A, but is not random to A prime. So I don't care about whether randomness exists or not. I want to know if it's useful. And this usefulness is an subjective thing. It's not an objective thing. Okay, what I can, so I have another line of this. Oh, yeah. So I wanted to also say this. Once you do this, you can do it for everything in BPP simultaneously, right? This idea will work for every A. I can de-randomize every A in the same manner. So I got like a general framework for de-randomization. I don't have to go problem by problem and think how to get rid of the randomness, and maybe primes are distributed this way and maybe geometry this way. No, I don't have to know anything about math, about the mathematics of this specific problem I'm trying to de-randomize. Yeah.
So this slide is actually saying that, we can just, to de-randomize, we can just build a theorem generator and we enumerate all the seeds instead of, enumerates.
Exactly. So I didn't talk about the seeds. You need seeds for this, but because I didn't tell you exactly what I evaluate f over. But the idea is that since f is something that A cannot compute, f of x will look totally random. What is x? I didn't really tell you. And you need seeds, and there are actually various types of pseudo-random generators in complexity. One is seeded. Oh, sorry. Okay. Anyway, yeah. For this kind of thing, you will definitely need a seed. Let me say that. Yes, you will. Definitely need a seed. The seed will be short enough, like in crypto, that you can go over the seeds. So we will get rid of this. So I didn't specify how to exactly do this. What is the x's you do this, but you can do this. And this is the idea. Again, it's the same idea as in the cryptographic construction, but I want to show you that it gives us something extra. It gives us de-randomization, and there is a trade-off between resources. Okay, what else do I want to say? Oh man. Okay, the last part of what I wanted to say, we have time for this, cool, is I wanted to kind of like a new thing that is happening recently in the world is that people are trying to take a computational lens on the sciences. And I kind of talked about before about can nature help us to understand computation? Is so bubbles solving NP hard problems or not? I want to talk about how computation can help you understand nature. And some of the papers I was telling you about that they're showing that there are NP complete problems in the different sciences are actually using this, are trying to show that to model their problems as NP or NP complete problems to say that those problems are hard, to kind of explain why something cannot be solved in their respective area. And I want to say that this can happen on a larger scale. This is happening on a larger scale. I want to give you some examples of what I mean by a computational lens. So again, we think of computation as something inherent, like gravity, like some consideration or limitation that you have to take into account, some rule of nature. Um, okay, so this is about modeling how you can model natural phenomena in a rigorous computational way. So the example I chose to present here is evolution. And we kind of have pretty good um, qualitative understanding of evolution. We scan the DNA of many animals. We understand the tree of this. We understand how it's supposed to work. We're pretty good at this. But there are some criticism. So this is one of the things that are being thrown against evolution. Evolution is as probable as a tornado assembling a 747 airplane as it passes through a junkyard. Okay. You see that and you say, no way, there's a tornado is not going to do this, and evolution. But to actually address this in a serious way, you need to think quantitative thoughts. So yeah, to assemble airplanes, tornado will be able to do this. Enough tornadoes. How many? Maybe exponential in the number of pieces you need. Maybe under reasonable model, right? Maybe every time the probability of having a new correct part is half. You can try to model this, but I want to say under reasonable modeling, this should take exponential time in the number of pieces or something. And to actually address such sayings, you need a quantitative explanation. How come our DNA, that is, if I quote it correctly, is about 4 billion bits to represent, how did it arise over roughly 4 billion years? You need a quantitative way, you need a framework, you need to explain this. How did it happen? So again, we know qualitatively, we know what's happening, but quantitatively, we don't have an explanation, or we're working on an explanation. So this is Valiant. He's like a very famous computer scientist. And he started this area of modeling evolution and other natural phenomena. And by now we have many people working on this. So evolution, so his modeling is, he modeled evolution as a learning algorithm, and you can try to understand the running time of this learning algorithm and so on. It's a kind of a Puckling, it's kind of a pack learning thing. It doesn't matter if you don't know what this is, but roughly what do we mean when we say a learning algorithm? I mean, there is a function f from some set of functions, and I get to see samples. Maybe I see x and the evaluation of f over x. So f is, I'm assuming it's taken from some class of functions. I know this class of function, I don't know f, and I see samples of this form, and I need to guess what f is. And you can try to model evolution this way, but it's kind of unclear what is f. What function is evolution attempting to learn? So this is part of your modeling. Maybe evolution is trying to learn f that is the best genome, which is a kind of a function of the protein production. So you can come up with function. And what are samples? Samples are if a person with genome X survived or had kids. And maybe the hardest is what is C? What is the class of functions that you assume F to be from? So it needs to be something rich enough to support complex biology, but something narrow enough to allow us to have an efficient learning algorithm. Some functions are very hard to learn, like SOR. Okay, anyway, you can do this. You can think about those things and fill in the details. And maybe you don't want to do PAC learning or restricted PAC learning. It's not exactly PAC learning. Maybe you have another model. I don't know. So people are working on this. What is a reasonable thing? How do you explain that evolution happens so fast? Okay, and it's not like a tornado. Again, it's pieces of philosophy, but you can actually do this. It's a huge problem. It's a huge, it has huge importance to humankind to understand those things, and those things are sometimes quantitative. And you can hope to model other things like your brain, right? Those are neurons. They're probably a distributed algorithm happening, and people are doing this. Computer scientists are partnering with labs, and they take scans, are trying to understand, trying to come up with models, trying to come up with algorithms. People are actively trying to do this, and this is, I think, a very worthy effort by the community. Okay, so this is one example. You can try to do other things, other big things, and refine your models and work with labs and with practitioners and try to see if you're right and come up with a good theory. I don't know if I have. Let me maybe quickly go to over the. I think this is the last slide. So this is again piece of philosophy. I just wanted to show how computational consideration can be taken into account, can explain some things. Okay, so these are again totally different. Okay, I'm kind of obsessing about primes I see in this presentation. Okay, but primes are important. This is the largest known prime, I think. I Googled this. Every time I need to Google this, but I think this is currently, it didn't change for the last few years. There's some associations that is trying to find those things. Okay, so they're trying to find primes of this form because they're like known primes. Good. So here is a piece of philosophy. What is a known prime? What does it mean that it's known? In what sense do I know this number? Okay, maybe it's known to me because this p is speaking a unique positive integer, and this integer was proven to be prime by computer software, right? It's distributed software. People help, and they checked all the options, and this is prime. Good. So okay, maybe this is what it means to be known. But if this is the meaning of known, that there's specific prime number, picks up a specific number and shows as prime. Here, let me give you a bigger prime. P prime is the first prime that is larger than P. Done. It picks up a specific prime, and it's obviously prime. It picks up the number, and it's obviously prime. Why is this not a known prime? I show you this, but you're like, no, this is not a known prime. Why? Now you can, again, this is philosophy. What is known, what is not known, but a possible explanation, again, this is, I think, by Scott. Here's a possible explanation. For this number, for numbers of the form 2 to the k, I have an efficient algorithm for writing them down, for computing. It's repeated exponentiation. So maybe it's known because I have an efficient algorithm. Maybe I don't have an efficient algorithm for this yet. So this is not known. Anyway, I don't know if I buy this or not. I want to put it up there to say that you can do philosophy this way, that this can be part of your considerations. And people were actually doing this, were actually taking into account computational consideration of hardness and easiness to do other things. I found this paper about the firewall paradox. I wish I can tell you more about this. But from what I understand, this is a paradox that kind of contradicts no cloning. There are no cloning rule in quantum computation. You're not supposed to be able to clone a qubit, and they show that something shows that you can clone a qubit. And this specific paper shows that is trying to resolve this paradox by saying that that the computational process that we require to do this is actually too long. So again, this is like a computational complexity thing that they show that the black hole will evaporate before. Okay, whatever. Obviously, I'm not a physicist. I can give you a link to this paper. But anyway, people are starting to do this, are starting to say computational things are something we need to take into account when we do science. Okay, we need to reason about how long and what's the computational power, and we need to take this into account. And this can explain stuff in physics, and it can explain natural phenomena, and it can explain philosophical ideas or philosophical paradox and so on. And I think this trend is growing now, and it's very nice because as I started the first talk saying, I do believe that computational complexity is underlying everything. Computation is everywhere, and computational power is something we really should be taking into account. And it's kind of weird that okay, it is done, but I would expect to see it in a larger scale. Okay, I think this is all I have. Let's see. Yeah, in time, yes. Okay, let me pause the sharing. Oh, I was sorry. I lost track. I was talking straight. Sorry. Questions? Again, I'm sorry. This was kind of philosophical because I kind of assumed that all the nitty-gritty details of, are you will have to take a class doing this. So no, I mean, there's stuff in the chat. Oh yeah, so there's some things about primes. Yeah, so the Miller-Robbin, what is linked is about those roots of one that are kind of unreal. They have some other tricks in the Miller-Robbin algorithm. So there's more than one way to prove if to certify that a number is a prime. I think there probably have a Wikipedia page and you can see different ways to assert to prove that the number is a prime, and different algorithms are using different tricks like this. If P is different than NP, then BQP is equal to P. Okay, I didn't read everything. Let me just try to parse this. So what do we know? So, okay, many people think that quantum algorithms can solve NP-complete problems. We don't believe in that. We don't know, but we do not believe in that. We don't believe that NP is contained in BQP. Wait, how do I see the chat again? And what's the question? If P is not equal to NP, then BQP collapses to P. I don't see why. Okay, but I didn't write this. So are there questions? Do you want to ask me? Yeah, please ask if.
Sorry, I have a question. In the
Sure.
first slide, you said that NP problems are the problems that have a polynomial time decider, right?
Yeah.
What
No,
if?
it's the polynomial time algorithm for checking.
Yeah,
Yes.
certifier. Yeah,
To
but
certifying, yeah.
what if that certifier is also NP? I mean, it would still be possible to solve the problem non-deterministically using that certifier and checking all the
What do you mean
possible outcomes.
the verifier itself, the function that verifies is
Yeah,
NP, so this is circular
yeah.
definition.
Yeah, I know, but what if we can define NP somehow else and then use an NP use an NP certifier to solve the problem?
I don't. Can you tell me again what is the definition of NP you have in mind? I can't say that NP is if you can verify if there's an NP machine that will verify.
For example, we
You need
can
non-deterministic Turing machines that will.
yeah. For example, we can define that NP problems are the problems that can be solved non-deterministically with a Turing machine, and then we use that Turing machine to and a NP certifier to solve another NP problem.
Okay, so you want to define a class, NP star, that will be the class of problems for which you can certify when you get a witness, there is an NP machine that will check it. But why can't you collapse the two witnesses? So one will say you can probably collapse the two witnesses if you write it as an undeterministic Turing machine. Right, the first one, so you will get a non-deterministic proof, right? And then you will have a non-deterministic machine that checks the non-deterministic proof. So the non-deterministic machine will take another non-deterministic proof. So I think you can just collapse this to one non-deterministic proof. The two proofs will go back to one non-deterministic proofs. But okay, but it's obvious that you know your stuff. Okay, good.
Thanks.
Nice. Okay, that's the nice thing about philosophy. You don't need to answer technical questions. Any more questions?
Two just quick logistical things here, I guess.
Yeah.
One, would you mind posting the slides in Slack?
Sure. I did put the previous slides on Slack, right?
Yes. Yeah.
Oh, it did come across. Okay.
Yeah. And then
I'll do this.
Is there a second problem set for this material?
Oh, I didn't. Yeah, I didn't produce a second problem set. Sorry.
No, that's
Can you work on the first one? I was thinking about this, but I didn't want to. This talk, I feel, again, was not so technical, and I don't want to ask weird non-technical questions.
Right. No,
but you know, if people want to do reductions and stuff like this, we can definitely do. But I didn't produce a second problem set.
Not a problem.
I think the first one was long enough.
Yeah. I think they have problems from other courses as well.
Okay. Yeah.
All right. Thank you.
Okay. Thank you, guys. It was a pleasure. Bye.
Thank you.